Oh, hello. Hi, shout out to Rude and Herb who are already in chat. Nice to see both of you around again. Hi to Mountain Ash. Oh, hey, people are in for a 2 o'clock Sunday maths live stream. It's a nice place to be. And shout out to some followers. We do shout outs. I tend to get followers during the work week when I'm not live. Anyway, shout out to Clean Puffables, KCAP Z, Delta Amy, Tommy the Plank, and Asher BHS. Thanks for the follows. We're up to 12 squared. Hi, morning to Mountain Ash, afternoon to Neutrino. I'm trying to learn where people's time zones are, not in a creepy way, just based on how people say good morning or good night. Hi, Maria. Oh no, I've learned it's Murray Eterna, right? With the AE is like one letter. I've been calling you Maria. There's a break in between. Anyway, right. Okay. My plan is there you go. Oh, I forgot. It's one of those AE letters. What's that called? Like a kind of diphthong, I think, for two letters at the same time, like Caesar. Anyway, my plan is to show you some more stuff about Fermat numbers, but the difference is that for work I've been doing Oxford Online Maths Club shows about primes and Fermat numbers where I have to look very confident and look into the camera and tell people about modular arithmetic and stuff that I know about. Whereas what I actually want to show you is where I got this from or why I've been interested in pseudo primes and Fermat numbers. And that's a lot less confident talking into the camera because it's stuff that I don't know really at all. But I'm trying to learn it. So I'm going to keep trying to learn it, and the way this stream works is that I just stream the learning process sometimes. Oh yeah, okay, right. It's I've been corrected. It's two vowels. Wait, what? What am I thinking of? A diphthong is two sounds. I've just got the wrong word. Oh no. I got my terminology wrong. Digraph. Is that we're all talking about the same thing, right? I'm learning English as well. This is great. Huh. Yeah, the root's correct. I'm wrong. What's a diphthong then? I've been saying diphthong loads. Like queen? Wait. Wiktionary. Wiktionary is backing me up. Maybe I just mean a ligature. Anyway. Yeah, a character consisting of two or more joined letters. Ligature. But maybe that's a kind of typesetting word? Oh, I'm learning. This is my Sunday afternoon learning. No one can take this away. So, I want to show you some notes from second year number theory. So anyway, maths. I just think this is a really cool couple of pages of some maths notes either way. Partly because right, so we're miles. This is miles into a second year course, so things have got a bit tricky. It's describing a primality test. There's the generalized Riemann hypothesis is on this page, which is exciting. And there's no proof of this theorem, and generate something weird. Oh, not that weird. Like, how many elements do you need to generate this thing? So that'd be nice. But then there's a starred section in lecture notes at Oxford. Star means not examinable. Which catches my attention because, hey, here's some stuff that the lecturer didn't have to include because it's not something they have to lecture, but they couldn't resist including it as just some sort of extra stuff, which is what I'm all about, right? This is basically, if you like, super curricular maths, but in lecture notes. And probably in the actual lecture as well, which is what I do a lot of work at the moment on super curricular maths. So it's nice to see it in other places as well. And it's all about Fermat numbers. And it's got a kind of funny punchline. So I'm just going to quickly show you this. And I'll try and point out bits that I would like to understand better along the way. So there's Mersenne primes, which are these ones, 2 to the p minus 1. And this exercise, by the way, if 2 to the n is prime, then n is prime, that exercise is in the further reading. I put that in the further reading for this week's Maths Club. So we post further reading on the Maths website, and sometimes some challenges or extra exercises. Anyone in chat want to have a go at that exercise from a starred section of some second year Oxford Maths notes? I guess the converse, the other way of saying this would be, if n is not prime, then 2 to the n minus 1 is not prime, and I think that's the easier way to think about it. So if n is composite, let's say n equals pq, say, with these things both bigger than 1, then 2 to the n is not prime, because I've gone for the confident play of just writing it out. So that would be 2 to the pq minus 1, dot dot dot, fill in rest of proof. And I think I might leave this as an exercise for chat at some point. So I personally understand this bit, I think, of why this has to be a prime. It's a bit like the thing Leo did on the stream on Thursday at Oxford Online Math Club. They talk about whether these things factorise or not. And there's this massive number that is prime. And then it says easier to test the number of the form NP for primality because of something called the Lucas-Lerma test. Lucas-Lerma test? Anyway, Lerma. Yeah, one of those. So it's like star for me to go and learn about this at some point because it sounds cool. The analysis is beyond the scope of this course, but not terribly difficult. Nice. Hi, Throshy. What up? Happy Sunday afternoon. We're learning about typesetting, English language, prime numbers a little bit. I'm skimming through some second year lecture notes in a kind of additional section they've included on Fermat numbers. Right, here's a different one. So this is the bit that I would really like to understand because it's related to the rest of the course notes. So these things are things for me to go and look up, right? Statement of this test and look up some Mersenne prime stuff. But the thing down here I happen to know is related to the rest of the lecture notes. So if I get stuck, I can read backwards and find out what's going on. It's quite often the case with this kind of learning from lecture notes that you kind of find something and realise you need to go back and understand it a bit more. I've jumped right in on page 33 because that's the page with Fermat numbers. People who saw any of the Quintic Quest, yes, that's what I'm doing. I'm doing the Quintic Quest again. I did a live stream last year where I just tried to learn stuff by staring at it on stream. It was a whole thing. I'll try and do a tiny bit of that. Maybe next week, more computer games. Right, okay. So something called Pepin's test. Pepin? Not sure. We're going to call that Fermat number n. N is prime if and only if, and then there's some mad thing to check. 3 to the power of n minus 1 over 2 is minus 1 mod n, which is quite a lot. Okay. So let's try and play along as this goes. So the first time reading through, we try and sort of play along with it, as much of it as you can. So it says here that if this is true, then certainly 3 to the n minus 1 would be equivalent to 1 mod n. I guess that's just sort of squaring each side. Right, so this is quite good because this looks a bit like a to the n minus 1 is equivalent to 1 mod n for this number a, which is a bit like Fermat's Little theorem. Fermat's-Lisp theorem says that if n is prime, then you can. This is true for all a. And what we've seen is actually quite a weak version of that, which is trying to do the converse and just for the number 3. So instead of checking for all a, we've just seen, 3 satisfies this equation. Maybe it's because n's prime. Conditions like this, there's a note here. Conditions like this do not imply that n is prime, even if they all hold actually, for all values of 3. But they've got this example that the smallest base 3 pseudo-prime is 91. Here's an example where 3 to the power of n minus 1 is 1 more than a multiple of n, but n isn't prime. It's 91's not prime, even though it looks really prime. So we're up to here at the moment. Okay, I think 91. So this is the smallest base 3 pseudo-prime. I think a base 3 pseudo-prime is one where it does that. And then a Carmichael number is something where if it's a pseudo-prime for all bases. Anyway, so it does follow apparently that the order divides n minus 1. So the order would be, the order is a number q such that, this is order n3, sorry. There's a q such that q, 3 to the q is equivalent to 1 mod n. And I think the smallest such q. Oops, I mean smallest such q. Smallest positive number such that when you do that power. Now this says it divides n minus 1. Do I believe that? We know that 3 to the n minus 1, so I suppose n equals 91 has this, but doesn't have that. So we don't know if this Fermat number might secretly be the number 91. It's probably much larger than 91, but you know what I mean. There's lots of facts about the order of something dividing something else. Yeah, it's something like the order is the smallest possible number that gives you 1 back. So then if you, by squaring it or cubing it, you can show that so multiples of q, 3 to the 2q will also be 1 mod n, 3 to the 3q will also be 1 mod n, and so on. So multiples of q. And then if you see some 3 to the power of something, like 3 to the k is equal to 1 mod n, then there are two possibilities. Either k is a multiple of n, or we kind of missed a bit. And I think if we missed a bit, then you can take the remainder. Hi, Neutrino. Sorry, this thing I listed over here for this order of n with 3 in brackets. I was trying to define it and I did it really badly, so I'm going to have another go. I thought I sort of got away with it, but I obviously didn't. This is defined as the smallest positive integer q such that 3 to the q is 1 more than multiple of n. And similarly, if this is a number other than 3, then you change it down here, and if this n is n matches up there. So it's like the number of times that you need to multiply 3 together until eventually you get back to 1 mod n. Fermat's-Lisp theorem says if n is prime, then eventually you'll get back around again. Hello, Matt here. 21. It's been a while. Welcome back. We're reading a tiny bit of some second year number theory notes. People who've been watching Oxford Online Maths Club from my day job will have noticed that there are some similarities between topics in this small section versus topics that have appeared recently on Maths Club, because I was reading this and then wanted to do content on pseudo-primes, content on Fermat numbers, content on primality testing. We will get there. Okay. So I think I agree with this because I've seen similar statements before, which is not very convincing for you, of course. There's sort of because it's the smallest positive integer, you can do some work there. So once you've decided that, I don't know, let's put a concrete number in for fun. Maybe you've decided that 3 to the power of 5 is the smallest example where 3 to the power of that is 1 more than a multiple of n. And you've checked the smaller number, so it's 3 to the power of 5. The order is 5, you would say. That's the order of 3 modulo n, let's say. Once you've done that, of course, raising 3 to the power of 10 or 15 or any other multiple of 5 will be just a whole bunch of 1s multiplied together. And then that means that the powers there are things ending in 5 or 0, so 5, 10, 15, 20, 25. If somebody says, oh, how do you know that 3 to the 26 isn't 1 more than a multiple of n? How do you know you found all of the examples where 3 to the something is 1 mod n? And that's not too bad, because if you're interested in like 3 to the 26, then you say, well, hang on, that's 3 to the 25 times 3 to the 1 mod n. And we just agreed that in my example, 5 is the order. 3 to the 25, that's 1 mod n. This right-hand side is 1 mod n. So this kind of left over bit kind of must also be 1 more than a multiple of n. 1 is always co-prime to n. There's a fact there. So 1 has always got an inverse mod n, so you can multiply by the inverse of 1 mod n. Is that true? What's the identity? What am I talking about? On the left, this is just 1 times question mark, question mark, question mark, and on the right it's 1. Yeah, thanks everyone in chat. The inverse of 1 is 1. Yeah, but Zooslander gives you a multiplicative inverse, thanks. Yeah, take the remainder of it. Thanks, Thrice Shy. 3 to that must be 1 mod n. Yep, here it is. This bit here is 3 to the remainder. Yeah. So I think that's convincing enough for me to say, aha, once you've decided what the order is, the order must divide any other example where base to the power equals 1 mod n. You just get the multiples and you don't get anything else. If you got anything else, you would have, fitting into the gap in my pattern, there's a kind of smaller interval where it goes from 1 to 1. 1, 1, 1, 1, 1 on this kind of ladder. And then halfway in between, is there a rung here as well? No, because then we can extend and infer the existence of smaller rungs. So there'll be a smaller example. That sort of argument comes up quite a lot in group theory, which is sort of what we're doing, I suppose. No, we're doing prime numbers. Okay. And there's also this example to say that here, by assumption, 3 to this large power was minus 1 mod n. So the order 3 doesn't divide this. And that makes me think that we've nailed down, how do you divide n minus 1? A factor of n minus 1, but does not divide n minus 1 over 2. There's something suspicious about powers of 2 here. And in fact, n minus 1 is a power of 2, because Fermat number's 2 to the massive power plus 1. So this bit we're using the fact that it's Fermat number, massive power of 2 plus 1. So now it follows that the order of n of 3 must be exactly this, because it divides n minus 1, but not, suspiciously, not this slightly smaller number. So we've got like 32 and 16. And we're saying, well, yeah, it divides 32, but it doesn't divide 16. And I thought it's pretty mysterious for a bit, because there's almost nothing that divides 32. Here's the sort of example of what we've got here. Divides 32, but not 16. What? Is it 2? No. Is it 4? 8? 61? No. It's 32. It has to be the large number, which kind of technically divides 32. Technically correct being the best kind of correct. Okay. So then there's some group theory to wrap this up, which I'm not sure I'm going to get to, but hey. Oh no, this is good. This says that... this is kind of mad. This says that along the way, as you multiply together all your threes, you've got to multiply loads of them together. So there are lots of different things to see along the way. Remainders modulate n. Ooh, theoretically correct. How about correct but unprovable or something? Or correct in if you assume some sort of large axiom. These are all good sorts of correct. So this is telling me that we can generate lots of stuff. This group, this notation means remainders when you divide by n, the kind of modular arithmetic, so just normal z mod nz means it's kind of the integers, but quotienting out the multiples of n. I think we had a diagram at some point where you imagine like the number line, but you imagine that the multiples of n are all the same. That's one way to build this kind of model of remainders. If you say all of these points are the same and addition works in a sensible manner, then you get kind of these points will end up being the same in this nice structure. And then the cross up here means just the things with inverses. There's some group theory to say if n is a prime number, then you get quite a lot of things have inverses. If not, then it's only things that are coprime to n that have inverses. We've shown that this thing has got quite large order, which means it's generating quite a lot of stuff along the way, sort of making new and interesting numbers, all of which are less than n and coprime to n. The only way to do that is if n is a prime. So this is kind of quite a cool fact. I like that a lot. So this would be enough to... So this would be enough to prove that a large Fermat number was prime, which is the exciting thing to do, right? The exciting thing to do is to plug in k equals 100 into here, evaluate the number, and then just check, is 3 to the power of that number, so to be clear, that is 3 to the power of 2 to the 2 to the k, over to, hang on, I've got a minus 1 from the Fermat prime, minus 1 and divide by 2, so I should put a divide by 2, which I think is a minus 1 up here. Is that minus 1 mod n? So you just check that for a large value of k, where I'm not being very clear about where that minus 1 lives. Divide by 2 up here. There you go. Just check that, and if it's minus 1, then bingo, we found a Fermat prime. That's huge. You'll need some clever ideas to actually evaluate it, but you know, good stuff. The converse is also true. The converse here is using some sort of quadratic residue stuff. Quadratic residue theory is maybe something I want to do. Wait, hang on. Thryshy is telling me you don't necessarily need the group theory. Consider 3 to the 1, 3 to the 2, 3 to the q. All of those have an inverse. Yeah, where q is the order. Yeah, and you're using the fact that yeah. I'm not sure you can say that's, yeah, I'm not sure you can say you're not necessarily using group theory. Maths. These will have inverses. The inverses bit, like naively at least, that sounds like group theory. Somewhere in there's a fact that if everything's got an inverse. Or am I being silly? Are you just telling me don't think of it as a group? I don't know. Okay. So I thought we could maybe go on a journey to try and understand. I thought we could maybe go on a journey to understand the quadratic residues, but it might take more than a Sunday afternoon. But that's my idea. Because going the other way seems clever. That's an Euler's criterion, and I can't remember these things. I guess it's going to be... So quadratic residue asks for which numbers a is there b such that b squared is equal to a mod n. So it's kind of, I guess, given n, quadratic residue mod n. And the maths of these things is lovely. There's this nice reciprocity statement that tries to switch around a being a quadratic residue mod a versus n being a quadratic residue mod a, which is what this is kind of doing. These are, the notation is not great, but these are not fractions and they're not vectors either. They're some sort of weird symbol that looks exactly like a fraction inside some brackets, but some symbol trying to keep track of whether this is a quadratic residue or not. I think I might show you that in a moment because I want to understand this a bit better. Right, and then there's some notes about mod 3. N is 2 mod 3. The powers of 2 alternate between 1 and 2 mod 3. Yeah, that sounds true because 2 is minus 1 mod 3. So powers of that alternate between 1 and minus 1. Minus 1 because we n is a huge power of 2. It's a huge power of 2 with an even number up there. Yeah, good. Okay. So wait, if you put an even number on it, you get minus 1? That doesn't look right. Let me check some small numbers. I've confused myself about whether you want an odd power or an even power up here. 2 is minus 1 mod 3, right? Oh, it's right, and 2 is an odd power of 2. 2 is an odd power of 2. Welcome to the show. Yeah, are these the wrong way around? These ones are squares. Yeah, Mountain Ash, the notation's horrible, right? Might try and do it in a second, but first I want to understand this bit. Okay, let me know in chat. Am I being daft? So this is talking about whether powers of 2 are 1 more or 1 less than a multiple of 3. If I put in j equals 0, or j equals 1, let's try j equals 0. Gives me over here 2 is not 1 mod 3. And over here 2 to the 0 is 1, which is not 2 mod 3. And if I put, I think these are the wrong way around. Right. And now I'm worried about this. So is n 2 mod 3? Yeah, n is 2 mod 3. Oh, okay, maybe they don't want to use negative numbers, that's fine. It's all equivalent, whatever. N is 2 mod 3 because the power is... I've really confused myself. So n is the number 2 to the k plus 1. So we've got this big even power of 2. When you have an even power of 2, that's a power of 4. 4's a 1 mod 3. This is 1 mod 3. This is 1 mod 3. 1 plus 1 is 2. Welcome to Chill Maths. So I agree with the conclusion that the n really is 2 mod 3. Good. We got say the line, Bart. We got the catchphrase in. Good. And then hopefully we'll get there and we'll understand what this notation means, and then what Euler's criterion are. So I think to understand this proof, all I need is an idea about the reciprocity law, which I tried to say out loud and it's on the page, hidden in amongst all my scribbling. And I need an idea about what Euler's criterion is. I think I remember what it is, but we'll get there, and I probably want to write it down at some point what a quadratic residue is. Right, well, how long have I got? I reckon I can understand this or revise this in about half an hour. At one point in my life, this was something I knew. Can I get there again in a Sunday afternoon? enough to understand this primality test for Fermat primes. Anyway, the reason that I want to do this is because I think it's cool, especially because of this beautiful comment down here. This test does not provide a useful way of finding large explicit primes. For the simple reason that probably none of these are prime. Which is just lovely. There's so many reasons why I don't really want to work out 3 to the power of 2 to the k minus 1 mod n itself, or like huge power of 2 plus 1. So many reasons I don't want to calculate that. I'd have to do clever things to do with powers of 3. But then also it's not useful because we suspect that none of these are prime. I guess that in terms of the test, if it turns out that these Fermat numbers are composite, then we will have a large supply of numbers such that 3 to the 2 to the 2 to the k minus 1 is equivalent to 1 mod 2 to the 2 to the k plus 1. If we want one of those, we could reverse it. Maybe. Maybe that's helpful or not helpful. I can't imagine wanting to solve this equation. And actually, maybe the proof of infinitely many composite Fermat numbers, maybe the proof that needs this fact or something. So we'd have to prove both at once or something. I guess this shows that they're equivalent. So, was that the thing on the stream on Thursday? Yeah, so Thursday was all about Fermat numbers. We talked about these things. And people sometimes ask me, where do you get ideas for Maths Club episodes? And here's the answer. This random small section of some second year number theory notes. We got 2 episodes out of this because it's got the word pseudo prime in it as well. So you do something like this, you read the pseudo prime bit and you think, ooh, I should look up pseudo primes. And that was an entire episode. And then you think, Fermat numbers in general, maybe we should talk about those. Fermat primes. Talk about maths we don't know. Okay, but my plan for today is to go a little bit deeper and try and understand quadratic residues. Just a little bit, I think. So this is a bad idea. It's going to involve a lot of modular arithmetic. I think some people learned about modular arithmetic for the first time about a week ago when we mentioned some on the Thursday live stream. If nothing else, I'm showing you what learning maths looks like. Let's back this up. Where are we going? What are we doing? Who am I? Where am I? So I'm just going to try scrolling backwards through the lecture notes until I see something that I want. Not this right now. Not this right now. Yeah, quadratic sieve. Not this right now. Fermat mention again. Factorization from chapter 5 is cool. Oh gosh, a big line down the side usually means that I want to come back and learn it. Concludes the proof. Yeah, this is it. This Euler's criterion. This is the reciprocity law. Okay. Let's read the reciprocity law. And that looks cool as well. Divide E into the following 4 sets. Sounds brilliant. It's a sort of counting argument. 4.2, what's proposition 4.2? Oh, yeah, here we go. It's called the Legendre symbol. And, okay, so it's got stuff about 2 being a quadratic residue, even only if prime P is 1 or more or less than 1 mod 8. And theorem 4.1. Ooh. Theorem 4.1. Okay, so we've got Euler's criterion here. So I'm going to need to understand this at some point. And there's this 1 mod 4 corollary. 1 mod 4 is interesting to us for Fermat numbers because almost all of the Fermat numbers are 1 mod 4. The first one's the number 3. That one's not 1 mod 4, but then after that they all are. So I think I'd like to try and understand this as well. Where did they bring in... Ooh, look, by Fermat's little theorem. That sounds fun. Where did they bring in the quadratic, the Legendre symbol? Is that happening over here? Yes, it's going to be further down this page. Okay, so this is the page that I want to be. This is the page I want to be on. And you can tell it's important because it's already got some of my scribbling on it from last time I tried to understand this. Right, good, let's get rid of that. And let's tidy this bit up down here as well. What is this? Oh, it's just me trying to write out the definition from the last time I tried to understand this. Okay. I think this is going to be a nice use of Fermat's Liouville theorem, actually. So this will be good for us. So let me try and decipher some of this for you. P is an odd prime, and suppose that A is in this set. Now this set means this is a kind of shorthand for A has a multiplicative inverse. So this set with the cross up here for multiplication, I guess, or maybe a cross to ban the things that don't have inverses, whatever. This is the set of things that do have a multiplicative inverse. Isn't that, hang on, P's prime, so that's all of them. A is not a multiple of P. Almost everything has a multiplicative inverse mod P. Because P's prime, so you can do Bezout's lemma or something to work out inverses. Primes are good for doing modular arithmetic because things have inverses. The group of units is nice and large. It's got size p minus 1, everything except multiples of p. Right, okay. So if A is a quadratic residue, this is awkward, isn't it? This A is a variable and that A is a word. One of them looks slightly larger than the other. I hope that doesn't cause us any problems. Right, let me try and read this. I know it's on screen. If you want to read the proof ahead, the proof stops down here, so anything I say to try and understand it is probably on the screen. I learned this a lot during the Quintet Quest thing. Quintet Quest, I'd be reading something and trying to explain it to myself out loud, and then I'd read down and see that almost exactly what I'd said was sometimes written on the page further down. But still, I think it's important to think for yourself when you're reading stuff, right? So if A is a quadratic residue mod P, then that means... what can I do with this? So some squaring? I can sort of see some squaring going on. Yeah, okay, and I've glanced down. There is some squaring going on. This thing is 1, and hence that thing is plus or minus 1 mod P. Why does that follow? Oh, so this is something like solutions to x squared 1 mod P. Oh, and we're maybe using the fact that you can do unique factorization if P is prime. So here's a kind of weird fact. No, you like this. This is standalone weirdness. Let's say you're looking for x such that x squared is 1 more than a multiple of n. Out in the world. And we're only going to check things between 1 and n, let's say. 1 works. We'll check things. Yeah, we'll check things up to multiples of n, because obviously adding a multiple of n to x would give us something like 3 plus 2n, and then the n's that mess around inside the squaring. There's a cross term, but those extra terms will be multiples of n anyway. So when you're solving things like this, you tend to just solve them for up to multiples of n. You might think that the solutions are x equals 1, x equals minus 1, I guess 1 more or 1 less than a multiple of n, and maybe more stuff. For example, if n is 8, then here are 4 solutions to that quadratic equation. I mean, it really is a quadratic equation, right? It's asking for x squared minus 1 equivalent to 0 mod n. It really is a quadratic equation. Here are some more solutions. So 1 squared is 1 more than a multiple of 8. 3 squared is 1 more than a multiple of 8. 5 squared is 1 more than a multiple of 8. And 7 squared is 1 more than a multiple of 8. This is awkward because it means that our quadratic equation over here, modulo 8, has 4 solutions up to multiples of 8, and they're all different up to multiples of 8. None of those differ by a multiple of 8, so they're all different solutions. So it's an example of a quadratic with 4 solutions. If you like, it factorizes like this. But it also factorizes like this. Mod 8. Both of these are mod 8, sorry. Which looks a bit cursed. That second one multiplies out because, right, the x squared term is there, and then the middle term with x in it cancels. There's minus 3x and plus 3x, that cancels. And then the leftover term is minus 9. But minus 9 is the same as minus 1 mod 8. So that's tricky. And then okay, so the minus 3 is the same thing as minus 5, and the minus 1 is the same thing as 7. So these solutions match up with those solutions. This is problematic. I would have gone for the oh no emote. It means that in general, if you're trying to solve, you've got polynomials mod n, they might not factorize uniquely. And it's actually a nice, thank you, Marie. It's actually a nice result that mod p, everything's fine. If you're doing things modulo p a prime number, then these things factorize just nicely. The only solutions are 1 and minus 1. Can I prove that? Not right now. That's code for I should remember how to prove this, but I can't remember how to prove this. Some sort of Eisenstein criterion thing. What are we talking about here? We're talking about this being a UFD. Is it a UFD for some really good reason, like it has I suppose it just needed to be an integral domain. No, I wanted to be a UFD. Right, good. Okay, ring theory. Let's leave the ring theory. I should be able to prove that. I feel like it's Eisenstein. I'm going to look it up later. It's probably Eisenstein. Okay. How far have I got? I realise that these are maybe the only options, but I don't see the link to it being a quadratic residue. You know, the way you could square something to get A. Yeah, if it's a field, it's a UFD. The polynomials are not a field because you can't divide by polynomials. But I take your point. Yeah, okay, it's going to work like that, isn't it? This is a field, and this is the ring of polynomials generated by a given field. I think there's some result in ring theory that I can't quite remember that says something like if you have a field and you make polynomials, then you get a UFD and everything's all right. But don't quote me. So some sort of fields to ring of polynomials conversion thing that I've kind of forgotten. Okay. Here we go. So p minus 1 is even. That's why they told us it was an odd prime. So you divide it by 2 and you get a whole number. And okay. So we're using this equation fact again to say how many roots there are for each of these equations. Cool. I like that, I think. What would a root look like? Oh yeah, these are really nice equations, aren't they? They're x to the d minus 1 and x to the d plus 1. Right, so in general, those things have only got a certain number of solutions each. All of the values of this satisfy one of these conditions, there must be exactly that many. Right, okay, and exactly p minus 1 over 2 values that do that one. Okay, they've all got to do one or the other, so it must be p minus 1 over 2 of each. Or I suppose all the solutions don't overlap, and they do cover everything. All of the p minus 1 values. All of the all p minus 1 values. Okay, so among the roots of these equations, you get everything. Maybe an example, mod 5? Yeah, example mod 5. So mod 5, we're looking at x to the d, where d is equal to 2. That's misleading because we're not actually looking at squares yet. Let's go mod 7. We're looking at x to the d. d is p minus 1 over 2, so 3 in this case. So we want to know, are you a solution to one of these or the other, mod 7. And there are 6 numbers to check, and the claim is that there's kind of 3 in each. So 1 cubed minus 1 is 0. 2 cubed is 8. Yeah, I had to think, but 2 cubed is 8, which is 1 more than a multiple of 7. 3 cubed is 3 cubed is equivalent to 9 times 3, which I'll change to 2 times 3 is 6, which is minus 1. So that one's true for 3. And then for 4, I think it's going to reverse and do this. 5 cubed, 6 cubed. I think it's going to go minus, plus, plus. So if I check all of these calculations, is 217 a multiple of 7? Yes, it is. 124 is a multiple of 7. Because... No, what is that? That's 126, sorry, I've added one. 126 is a multiple of 7. This one, 4 cubed is 64, take away 1 is 63. 27 plus 1 is 28 is a multiple of 7. Right, cool. So you can always add 1 or subtract 1, and there's an equal number of each. Because these are solutions to cubic equations, all of these are mod 7. Okay, it's a kind of nice demonstration. There's no obvious pattern to me going on there. Minus, minus, plus, minus, plus, plus. Probably the sort of thing people study, but what's going on? Are you supposed to add 1 or subtract 1 to get to a multiple of p when you do things to the power of p minus 1 over 2? It's 50-50. Your pattern will have just as many pluses as minuses in. Not obvious to me which ones are which. Let's hope it doesn't matter for this proof, because there's only about 3 lines left. Exactly. So, okay, so smiley face for this. They've got to solve one or the other. Okay, so if a is a quadratic residue, this has got to come in somewhere, hasn't it? Then a is x squared, and hence a to the p minus 1 over 2. Okay, so do the big power to find out which one of this it is. Oh, I see, I'm being silly. So up here I said I can't see where quadratic residues are going to come in. So I should have really written a as x squared for some x. And that's a bit like squaring as well, because that will put the squares go inside. So x to the p minus 1. Right, Fermat's little theorem, that's 1. Right, hang on, yeah, okay, so if you're a quadratic residue, there you go up like this. Right, you've kind of got an extra factor of 2 in the power hiding somewhere. Oh my goodness. There's Fermat's little theorem on squaring afterwards, and there's Fermat's little theorem for kind of squaring before, halfway through. So if a is x squared, there's kind of already got some squaring going on. And secretly what you've got must be the number 1. Okay, right, good. Okay, because it's it's something else to the power of p minus 1. Fermat's little theorem is brilliant. Anything to the power of p minus 1. I'm suspicious of that. He might not be quite enough power, but what if a is x squared, not r, right? That's the rest of the power that we need. Good, okay. What about the other ones? I suppose these are not quadratic residues. Yeah, okay. Not quadratic residues. Those are really nice. Quadratic non-residue. So you just check. You go sort of halfway to Fermat's little theorem. I'm writing that down. I'm pretty pleased with that. Halfway to Fermat's little theorem. If it's 1 already, that's a quadratic residue. It's a bit like trying to find the square root of a number. Mod p. Which is not as bonkers as it sounds. It sounds kind of bonkers. But trying to find the square roots. Yeah, I guess, is this a different way of guessing how many there's going to be? Let's try and square this circle. So when you're looking for quadratic residues or trying to analyse quadratic residues, I guess what the question you're answering is which numbers from 1 to p have a square root modulo p? Can I find something else that squares to give me that number mod p? And there's a little bit of a weakness here that, well, if x is a square root mod p, so is negative x. The equation x squared equals a is a quadratic, and quadratics mod p are nice. They have at most two solutions. So there's no more solutions. But this means, I guess, that you square the first half of the numbers, and then when you square the second half of the numbers between 1 and p, you're just going to see the same stuff again, but written backwards. So a sort of pattern to this, because the second half is like instead of p plus 1, it's like p minus 1, p plus 2, p minus 2, reading backwards the other way. So when you're doing squaring, it's like squaring a negative number. That means that things come in pairs. You can't have everything being a quadratic residue because there aren't enough square roots to go around. They come in pairs. So half the stuff is quadratic residues. Does that make sense? Yeah, they can't overlap either. You can't have lots of things square to 3. You can only have 2 things that square to 3. So you've got to have half the things get hit by the squaring function mod p. This is really weird. Let's write down another example. I think I'm going to go for the larger prime, like 11. I'm just going to sort of push. So mod 11. Let's look at some squares. 1 squared is 1 mod 11. Welcome to the show. 2 squared is 4 mod 11. 3 squared is 9. These are all going to be mod 11. 4 squared is interesting because 16 is equivalent to 5 mod 11. 5 squared is equal to, oh my goodness, 25 is 3 mod 11. 6 squared is 36, which is 3 mod 11. And I think it's already happening. Look, 49 is 5 more than a multiple of 11. 8 squared is 64, which is, oh gosh, I don't even know, 9 mod 11. Oh, adding it's hard. 64 is 9 more than 55. Yep, good. 9 squared is, I'm also now using the pattern a tiny bit. 81 is 4 more than 77. 10 squared is 100, which is 1 more than multiple of 11. And then I guess for completeness, I want to write down 11 squared. 11 kind of doesn't really fit into this because 11 is not co-prime to 11, but just for completeness, right? And so there's this nice pattern: 1, 4, 9, 5, 3, 3, 5. What a weird 5. 9, 4, 1. It's like plus or minus, yeah, it's like plus or minus 1, because, for example, 9 squared is equivalent to negative 2 squared, mod 11. There's this nice, multiplication just works. If A and B are equivalent, and if C and D are equivalent, then A times C and B times D are fine. So you can do this kind of switching before you do the multiplication, which is sometimes a really good way to progress if you actually have to do a bunch of these. -3 is much nicer to square than 8. Anyway, observation, we've hit the numbers 1, 4, 1, 3, 4, 5, 9, 1, 3, 4, 5, 9, which is exactly half of them appear on the right hand side. 2, 6, 7, 8 don't, and I've missed 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 10 doesn't appear. Just got a weird pattern. Half and half. Yeah, some group theory going on. But more than that. Or maybe, I don't know. Can you say more than group theory? I don't know. I don't know the generalization of quadratic residues to other groups. I don't know how that generalizes at all. Looking for elements that square to a given element. Yeah, no idea. Something to look for, I think. Okay. So if P is an odd prime, then we get this rather nice result, which says if P is an odd prime, then we get this really nice check for whether or not you're a quadratic residue, which is to go halfway to FLT. And then check if it's 1 already. Okay, that's Euler's criterion. Quick check of how that fits in. My understand this in half an hour has not happened. I'm not doing this proof, am I? It's just not going to happen today. Back into the thing where we were trying to understand this. Okay, in here. Right. This whatever, this quadratic residue or whatever, is being -1. That's kind of something is equal to -1, which says it's not a quadratic residue, or no? Yeah, I don't see the link, right? Suppose that n is prime. Oh, right, hang on. So if n is prime, what we were just doing, we said that if something's prime, then this thing to the power of p minus 1 over 2, exactly the right power, right? If n is prime, then you should be able to plug this in. So long as 3 is not a quadratic residue mod 1, we've shown. So it must be true that by this point somehow we've shown that 3 is not a quadratic residue mod n. Okay, oh, and I can kind of see 3 quadratic residue mod n is what this symbol means. N is quadratic residue mod 3 is what that symbol means. n mod 3, 2 mod 3, okay. Is 2 a quadratic residue mod 3? No, it's not, because 2 to the power of p minus 1 is 3 minus 1 over 2. 3 to the power of... Is 2 a quadratic residue mod 3? It's obviously not, because 1 squares to 1, 2 squares to 1, that's it. 2 is not. But there is a test that we saw by Euler's criterion, where you could raise 2 to some weird power, possibly just 1, and notice that that's the number -1. Right, okay. Whew. It's funny, you learn a new trick, and sometimes you want to use it all the time to say, oh, is 2 a quadratic residue mod 3? And the answer is kind of, well, you could go and take 2 to the power of 3 minus 1 over 2. You could go and try and work out what that is, mod 3. Or you could just say, well, the quadratic residues come from squaring 1 and 2, and those are both equal to 1 mod 3. So no. You learn new technology, and it's very tempting to use cool technology to achieve everything, but we're not quite there yet. So we just need to check then that 3 is not a quadratic residue modulo huge Fermat number. And there's some tricks for that. One of them is called quadratic reciprocity, which I would like to learn now. It's so powerful just being able to grab the lecture notes and try and learn stuff. Thanks for joining me on this weekend of learning. And the notation of Lemma 4.2, which I haven't read. I hope it doesn't come back again. And this is going to give us a proof of Lemma 4.2. So if I ever need to go and read Lemma 4.2, I now have seen a proof. Brilliant. Here's a follow-up. Corollary means follow-up or a following bit of maths. Here's my prime. -1 is a quadratic residue mod p, if and only if p is 1 mod 4, because p minus 1 over 2 is either even or odd. If if it's even if, oh my goodness, why is this so hard? Even if P is 1 mod 4. And it's odd if, oh gosh, is it odd if P is 3 mod 4? Yeah. P is 3 mod 4. So we've raised this thing. So if you want to know about -1, A equals -1, you're taking -1 to an even power or an odd power. And the way that minus signs alternate, as you do powers of minus signs alternate, the way that works also works in modular arithmetic. So you can keep going. And this says that you'll hit 1 if P was 1 mod 4, and you'll hit -1 if not. Okay, that's kind of nice. Let's learn the Legendre symbol. It's defined like this. If A and P are coprime, and if, okay, so the condition we had before, A and P are coprime, there's so many use of brackets, it's out of control in this sort of maths, right? So we're introducing a new sort of bracket in terms of this one means the numbers are coprime to each other, and this one means modulo P. Anyway. And if A is a quadratic residue of P, -1 if it's not, and 0 if it was a multiple. For example, 23, we're going to define this symbol to mean what the number 1. It's really off-putting, I think, seeing 23 divided by 7 and saying, well, 1. But that's just code for saying that 23 is a quadratic residue mod 7. I suppose we're doing all these things A mod P. So I've been talking as if 4 squared is 16, which is 16, which I've been simplifying down to like 2 mod 7, but this is 2 mod 7 as well. So yeah, fine, okay. The 23 is a quadratic residue mod 7, fine. Anything, 30, 37, all of them. Quadratic residues mod 7. I guess if you're working mod P, then you have to accept all of these things, not just the small numbers. We've got a formula for this, right? Because we know that A to the P minus 1 over 2 is equal to, well, I guess mod P. Yeah, we've got a formula mod P, right? It's something to do with A to the P minus 1 over 2. Basic properties. Legendre symbol does this. 1 is always a quadratic residue mod P, because 1 squared is 1. A to the, I was the thing about 37, I was just saying, there's a mod P fact, you can add KP upstairs. This last one, yeah. Consequence of lemma 4.2. No! Oh, right, hang on. So this might be 0. Yeah. Horrendous joke about fractions, vectors, and quadratic residues. Yeah. Who would do a joke comparing terrible notation to other terrible notation? For example, we're using this. Some people use this for vectors, and some people use this for binomial probabilities. We're sort of overloaded on notation that uses brackets. There's way too much of it. It's also, I don't really love it being called a symbol. Yeah, cheesing. As a symbol, I guess. We don't call very many things symbols when they're built out of fractions and stuff. Like 3 over 5. Are people calling that a symbol for the concept of 0.6? I don't know. Wait, anyway, names are very confusing to me. I think maybe I think about names too much. This last one's fun. If one of them is divisible by P, then both sides are 0. Ah, okay. So they're coprime to P. You've got to remember, almost everything is coprime to P. So if we've got primes P, yeah, okay. Almost everything is coprime to P. So if these things are coprime, then what's going on? Say lemma 4.2. I think it's time for me to look at lemma 4.2 briefly, and then decide it's a consequence of Euler's criterion that we just worked to understand. Where is lemma 4.2? I thought it'd be around here. Oh no, I don't understand these notes at all. What is going on? What's all this? I'm nowhere near the place I wanted to be. What is this? Lemma 4.2. The product of two quadratic residues is a quadratic residue. Yeah, multiply together their square root things. Product is quadratic non-residue because of division or something. product of two quadratic residues, non-residues, quadratic residue. Oh, okay. And this is just the thing we've seen now is you can test all of these things by doing some sort of multiplication. If they're non-zero, then it's like plus or minus 1 for whether these things, the values are equal to these mod p. When you do these powers, and then both sides will agree mod p. So if you simplify them down to be something like you take the values of these things and multiply them together. No, that's not quite right, is it? What did I read over here? I read something like this down here. Yeah, it's the thing. AB downstairs. Notation joke about sine inverse. Oh yeah, right, thanks. So sine inverse should be. But this means. So we've overloaded notation here in a really unhappy way. That this one means you do sine multiplied by itself a certain number of times, and this one really does not. So if you get used to this notation to mean the inverse function, then maybe this one should mean sine of x. Right? It should mean do sine twice. If that means undo sine, it should mean do sine twice. But that's not what people mean by it. And when you get used to this notation for sine squared, you sort of think, right, so this should mean 1 over sine, right? That should be what this means. This is why some people use arcsine. It's why some people write this. Because you can't, if you have both, you can't do any jokes. Oh, you do that one up. Okay. Yeah, square it afterwards. But then squaring is also a bit weird. We don't really have a symbol for the function of squaring. If we did it, would be like this. If you want to like squaring something, like we have names of operators all the time. Like if you want to distinguish between the values of a function versus the function itself, so you might say f of x is the value when you plug in x. Do people say R shines without the C? Oh, cool. That seems like a Google search waiting to happen. Inverse hyperbolic functions. Notation. Oh my goodness. You're right, the ones on Wikipedia have got not the C. Ugh, I've never noticed that. I guess I don't use those. Wikipedia is all like this, but without the C. Have I just been... These like inverse... Is there definitely a C in inverse trigonometric functions? Yeah, they definitely got C. Okay, mystery to me. Hello, XT Force 1. That's very loud. It's about 50%. It's about 50%. It's really good. If you've got a group of 23 people, it's brilliant. You might think that it should be really small because 23 is way less than 365. But the key comparison is that 23 is about the same size as the square root of 365. And this kind of like coincidence, when you select things from a group of, you call like D options, you pick n of them, you tend to get clashes if n is bigger than about, so roughly bigger than square root of d. It's called the birthday paradox in general. And for 365, the square root is about 20. So that's roughly when it crosses over. You can work out the probability, like you work out the probability explicitly for 23 people in 365 days by imagining the people arriving one at a time. First person arrives, everything's fine. Second person arrives, and they've got to, the probability that they have a distinct birthday, it's one of these. And you keep going. The second person, it's still pretty likely that they've got a unique birthday, and the third person and the fourth person, it's still pretty likely that they've got distinct birthdays. And surprisingly, I mean, these numbers after 23 we're going to get down to 6342 over 365, I think. Oh, I might be at 1, 2, 3, 4, 5. I'm out by 1. It's 343. So we're getting down to quite large numbers. 343 is still pretty close to 365. But then the exciting observation is that this is about 50%. And this drops off. Even though all of these fractions are pretty near 1, there's quite a few of them, and they differ by a little bit. Maths fans, you know facts about this sort of thing. It's not quite this, but it's roughly. There's something related going on. So you can try and put that to good use. Good, okay. It's not this because the numbers up here are also changing, and they're not all the same. You can do some maths. Okay, I think we talked about it on my other show at one point. What am I doing? Nice to help, XD Force. Thanks for joining, chat. Forceful by name, forceful by volume. Right, good. Okay, maybe I shouldn't encourage all caps, but it was good fun. Right, okay. Here's the amazing reciprocity fact. Oh, it's vanished. Where's it gone? There it is. There it is. It's tea time. Thanks, Barry. Reciprocity is brilliant. Main aim is to prove this: that if you've got distinct odd primes, you can flip them together, or you can kind of multiply them together, and you maybe get -1, or you maybe get 1. This way of writing is just mad. I guess what have we just seen? We've seen that if P and Q are different primes. No, we've seen that. We saw something about 1 more 4 and -1. No, we saw something about -1 being a quadratic residue. Whether or not -1 is a quadratic residue, but that's not what's going on here at all. Right, time for a cup of tea. And yeah, it's about 3 o'clock, isn't it? So time for a cup of tea. Thanks, Mary. I'm going to put the kettle on. I'm going to let you look at this. I think I'm going to run an ad break. If you're not coming back after the ad break, then that's fine. Have a nice Sunday. I'm coming back after the ad break to try and read some of this proof. I'll be back in a minute or so. Remember, if you see an advert, you are supporting charity, because this live stream is constantly in charity mode. Right, cool. See you in a minute and a half. I'm really sorry if the ads are loud. I'm told that Twitch ads extremely loud. So take care. I'm pressing the button now. See you in a minute and a half. Ah. Ooh. Mary had 2 adverts. I feel a little sorry for you. You redeem the tea time. I get a nice cup of tea. You get ads. Right, do I need to press a button to say that? Oh no, not report it. Blimey. Almost accidentally reported that as bad. Yeah, I don't know how to do that. Good, okay, good. There's a button market is completed. Thank you, it's my favourite mug. Oh, that's a good fact, Melton Ash. I love a dice fact. N 6-sided dice, more likely to get N different values than you are to have them all the same. Oh, right, well, all the same sounds impossible. Oh, unless N is 7, because you can't have 7 different values. 6, so if I roll 6 dice, you're telling me all different, more likely than all the same. All different is permutations of 1, 2, 3, 4, 5, 6. So that's like 6 factorial. All the same is, I don't know, 6 ways to do that. This is way more likely, right? And then maybe I should check the 1, 2, 3, 4, 5 cases, right? For 1, equally likely, certain. 2 dice? All different, all the same. Yeah, different feels easy with small numbers of dice as well. Yeah, I'm overthinking it. What about if there's not 6 sides? I think the way I'm thinking of it, it feels like n factorial is way bigger than n. That can't quite be right. Being different has got loads of entropy in it. Yeah, there's really not very many ways for them to all be the same. Okay. If you draw 2 cards, this is what we're thinking about for poker, right? If you draw 2 cards from a deck, you might get 2 of a kind, or you might not. Yep, good. Okay. Let's read some propositions. I don't think I'm going to understand a proof of this today, but I might read some fun maths if I keep reading. Sometimes you see fun maths and you actually get something else out of it. Right. Also establish the following statement about the nature of 2. Ooh, so if P is 1 or more or less than a multiple of 8, rather than being 3 more or less than a multiple of 8, then you get this fact. And there's an example messing around with the numbers 101 and 163. There's a break here, I think. This is the end of the proposition, and then this is a different comment. Let's check some small primes. So number 2 has a kind of square root. Do I even believe this? If P is 1 more than a multiple of 8, so for example 17, find x with x squared is equivalent to 2 mod 17. That feels impossibly difficult. No, it's 6. Because 6 squared is 36. Huh. I'm never going to guess the number 6. Is there some cool relationship between 6 and 17, right? Is there a formula for square roots? It's quite a nice. I guess the nice thing about modular arithmetic, really, maybe one way of saying it, one nice thing about modular arithmetic is that it lets you do things that are a bit like division with whole numbers. So you never have to bring in fractions or messy real numbers or stuff, but you can do things that feel a bit like division or solving equations. That maybe in the real numbers you invoke all these real and complex numbers. Hey, oh my gosh! You changed your Twitch, you didn't know? I didn't even know that was a possible thing to do. welcome to stream. I'm trying to learn number theory. I've done some number theory for work, and there are some bits I understand that got turned into Maths Club episodes because they're kind of understandable. Some bits I don't understand, which get turned into chill maths. Chill maths is me failing to understand things. RFL. Yes, there's a mad fact that 2 has kind of got a square root in modular arithmetic if you're working mod p, a prime that's one more or one less than a multiple of 8, which is half of them. Good, cool. It's been 5 minutes since an ad break, so Twitch has told me that the ad machine is reloaded, ready to go again. I've put a big line down the side of this, which makes me nervous. A large line down the side is my code for I haven't read this. The first time I skim through, it might be like, I'm not reading this now. Come back to this. So when I see one the second time through, probably time to read it. Let's read Gauss's lemma. Oh, Gauss, very clever. Mumbling to myself about Gauss is the content we're all on Twitch for. There you go. It makes it easier for me as well. I'm going to remember who's who. You put capital letters in so that I can see where the words start and stop. This is great technology. Herb's got a capital letter. Who else has got capital letters? Like nearly no one else has thought of Streamlabs. Capital letters. Great stuff. None of us thought of capital letters when we were 10. Right, okay. This is me talking about usernames and putting off reading Gauss's lemma. Let's go. P is not prime. IB a subset of the units, the things with inverses, or P. So some set such that, oh my goodness. This is the disjoint union of I and minus I. Oh gosh, okay. So you pick some numbers. Here's 0 on the number line. This is not going to be a good picture. It's P minus P. I guess you can pick some things, but then the mirror image needs to be all the stuff you didn't pick. The mirror image needs to be the opposite. So that I, the set of stuff I have picked, my coordination is not very good here. I, the set of things I have picked, and minus I, cover all the options? Not sure about this. Have I messed up? Maybe messed up. It's not obvious that I haven't drawn it very well so that they look like they're different. Yeah, we're not gambling on me understanding things. It's too easy for everybody to bet on me not understanding and then being incentivized not to be helpful. I've learnt my lessons from prediction contests where Twitch can be against me. Like that time, who was it who found a multi-perfect number but wouldn't tell me? Was it Herb? Was it somebody found a multi-perfect number and then wouldn't tell me because of a bet? Yeah. Zoe's here, keen on gambling. Okay. AB, an integer coprime to T. Okay, just choose one of them. Oh no, well, it's kind of switching between talking about A being a member of... Sometimes when we use the letter A, we're using it as an element of, in here, mod P, modular world, and sometimes it's just a whole number. And it seems like the Legendre symbols are accepting... Legendre symbols are accepting integers, which makes me grumpy. -1 to the power of T, where T is the number of J and I such that Oh my goodness, aj is in minus I. What on earth, Gauss? What on earth? What on earth? You want me to take... This is true for any set I. The set I... Oh no, yeah. Because this thing is just... The Legendre symbol, A of B, is a quadratic residue mod P. 1 for yes, -1 for no. And this says, ooh, it's either 1 or -1. What you should do is just choose your favourite set I of about half the things, so that I and minus I cover everything between up to multiples of P. I've lost the same game of chess twice. Is that like duplicate chess? Oh, did you play against yourself and lose from both sorts of... No, don't worry about that. Did you... Yeah, play a kind of mirror image of yourself. No, never mind. Reversing all of your moves so that you can lose in the mirror universe at the same time. Right, putting off reading the proof of Gauss's sliver. Why does the screen do that sometimes? Okay. Count them. Is this in minus I or not? The union is I. Oh my goodness. A is co-prime to P. So when you multiply I by everything in I by A, you get a shuffling of everything that's in I. Oh no, everything that's in... bother. No, because I is only half of the elements. If you multiply... So these contain everything, which I guess is like saying that HI... J minus, I don't like it. I don't like it, Gauss. Those J for which A multiplies you into the shadow realm, and those J for which A multiplies you and you stay in I. Oh, this is the... Sorry, that's obviously terrible. I'm really sorry that happened to you. But also, that's a thing, right? With that sounds like a... What's that computer game people are always talking about? Like multi-dimensional chess with time travel. It's a thing on Steam. You can play chess and you can branch the timelines. To win the game, you have to win in all timelines. I think your opponent can also reverse time. I don't know. It's the sort of thing that people do. Yeah, I'm just trying to refer to minus I as the shadow realm. We're gonna get there. Gauss, do you mind if I just choose easy examples, like I is 1 up to P minus 1 over 2? Is that all right with you, Gauss? Do you mind if I do that? Because it feels like it doesn't matter what I is, what the set I is, for your final result. So maybe I could just always imagine I to be this set along the way. 5D chess, that's what it's called. Maybe. We claim that multiplying by A and minus A, again, their union is I. I'm not awake enough for this. Disjoint because, yes, I believe that. From the definitions, these things are both contained in I. Yeah. Oh, look at the size of the sets. Okay, they don't overlap. their union is the whole thing, because they've got the right sizes. Can you keep going? Is that what we're going to do? No. Oh my goodness, the product of the elements. This reminds me a little bit of the proof of... There's a proof of Fermat's Little theorem, which involves multiplying together a whole bunch of elements. I don't think I've done it on the show, but whatever. So you multiply everything like this and everything like that, and that is magically the right power out the front. -1 to the power of size of j minus, because minus signs over here, I guess. Here's all the minus signs. 1 for each element of j minus. Brilliant. And there's loads of a's around. I'd have thought there'd be more a's than p minus 1 over 2. I can see a lot of a's on the left hand side. J minus and j plus gives I. Oh, but I is only half the elements. Yeah, okay, there's that many a's. Right, product of j in your set I. Oh, I don't like that. Oh, because the union is... Right, okay. Oh, okay. Product of everything. Cancelling that, which is co-prime to p. What? Is it on both sides? No, what? Where did it go? J and I of j. I'm really lost as well. I don't know what's going on. There's a square at the bottom. My plan is to get to the square and start working backwards. Cancelling. Where's the other one? Cancelling is what I say when it appears on both sides, right? Gauss is too clever. Just too clever. Co-prime to p. It's being multiplied. Yeah, it's being multiplied, so we're going to try and multiply by the inverse. What is all of this? Oh, this is the product of the elements of I. And this is the product of elements of I as well. This is like some really weird way of writing the product of the elements of I. You multiply together. Oh my goodness. Oh my goodness. J minus and J plus constitute all of the elements of I. No. Because we're not just multiplying the J's together, we're multiplying these A's together, right? So this is this fact that minus AJ minus and AJ plus. That's giving us these things. That's I. Everything in J minus multiplied by negative A, and everything in J plus multiplied by positive A. Yeah, okay. And then you get a whole bunch of A's, because you took everything from the set I and you multiplied it by A, and maybe minus A. And you got back, well, okay, things in J minus and things in J plus. Where do these things come from? Well, J minus and J plus are still disjoint, and I give you I again. I really feel like this is written right to left. You know, things get more complicated on the left, so maybe I should write it out backwards. Or just I would understand it better the other way around. Let's find out. So reading it the other way around is something like you take all the elements of I, and you multiply by a whole bunch of A's, one each. Everybody gets a multiple of A. So everybody gets a multiple of A. So you could think of this as being some stuff in here in I belongs to J minus, and some of it belongs to J plus. I don't like how many sets there are. There's so many. There's I, which is like half of the numbers, and then J minus and J plus are like, is it half of each of those? Probably about half of each of those. Yeah, probably half of. I'm not sure we've done the cardinality of each of those. Never mind. I'm about the same size. So here's a whole bunch of minus signs. Because when you multiply by a, you're going to get some stuff in I and some stuff in minus I. Yeah. Doing an example might be nice. Might be nice. I have to follow through for... Here's the size of that set. 3:30. I think we've got time to do it. Let's clear some space. Just a bit of space. Ah, look. Gauss's lemma is invariably applied with this set. When we speak of Gauss's lemma, we'll assume this choice has been made. But we're going to use that set. Okay. Here we go. Let's choose a prime. How large a prime shall I pick? We tried 7 earlier. That feels about right. I think these things are going to get divided into smaller sets. I want there to be quite a few of them. Yeah, okay, so we'll take p equals 7 and just see what happens. So we'll take I to be the set, slight abuse of notation, but 1, 2, 3, kind of mod p. But minus I is equivalent to this. It's not really how notation works, but never mind. It's kind of 4, 5, 6, mod 7. Hi, Brute Quill. Welcome to chat. You're wearing a little crown. What's going on there? That says you have Prime Gaming. Welcome to the channel. We're trying to understand a result by Gauss, which is all about prime numbers. So, you know, great maths. Everywhere you look. Okay, we need to choose a number for A. At a cool suggestion, we are doing a concrete example of all of this stuff at the top of the board. So let's choose a number. I'll take a suggestion from chat. Chat, could you give me a number between 1 and 6 inclusive? Dealer's choice. Probably not 1. 1's going to be easy. Maybe 6. Yeah, I feel 6. Oh, you've got exams. Good luck with your exams. You want some complex, like complex numbers? What do you need to know? There's quite a few people here in chat who can maybe help you as well. So we'll see. If you describe what sort of stuff you've got to do. Complex numbers. I haven't changed the stream title. Oh yeah, it's got natural number game in it. Thanks for spotting that, Neutrino. Do you remember how I changed it last time? No. Okay. Sorry if anybody's following for the natural number game. It'll come back at some point. I've got about half of it still to go. Maybe more. Future someday, but prime number mood sort of today. Okay. So Gauss wants to consider the following sets: J minus and J plus. J minus is the set of things in A. Hi, pretty cool. Thanks for the follow. J minus is the set of things in I, which is set 1, 2, 3, such that AJ is in minus I, and J plus is the ones over there. So I guess I should take I, this one, multiply everything by 6. Okay, so AI is equal to 6 mod 7. 6 times 2 is 12, which is 5 mod 7. 6 times 3 is 18, which is 4 mod 7. Kind of mod 7. There's going to be mod 7s kind of everywhere. Like that. So J minus is the set. Oh my goodness. J minus is the set of J in I such that AJ, which is all of them, I think. Have I got this right? The follow notification is the default follow notification. All other streamers have changed it to something bespoke to their channel. I haven't done it yet. It also plays a noise, but I don't think I'm broadcasting the noise to you. The noise is for me. You're allowed to say it's cute. It's just the default that happens when you enable Twitch alerts and think, that'll do. That's the level of effort that I've put in. I'm not sure I'm getting this J minus right. J and I, such that AJ is in minus I. For me, that's all of them. And J plus is those J and I. Oh, you get the noise. Ooh. It's not in my sound desk. My audio mixer doesn't know about that. Okay, good to know. Thank you. Okay, so this was handy because I was imagining these things to have the same size as each other, but in fact, with Herb's choice of 6 and this choice of I, for our choice of prime, P is 7, A is 6, I is 1, 2, 3. For that choice, I think J minus is all of them. And J plus is the empty set. In our example. Yeah. I think. Which maybe means it's not going to be a great example for the next bit, but whatever. Let's just see if we can follow this through. So it's the kind of claims. It's the stuff in the paragraph. The calculation, fine, whatever calculation. But it's this claim that minus AJ minus and AJ plus. I think I must be wrong. Yeah, I must be wrong. Because my examples here, AJ plus is the empty set, minus AJ minus has only got 3 things in it. Yeah, okay, so I think I'm wrong. Yeah, I've calculated 6J. Those J and I, their union is I. Yeah, I's got 3 elements. These things can't be the same size as each other. These things can't be the same size as each other. They've got 3 elements each. Right, so there's these new things we're calculating. Minus AJ minus and AJ plus. Minus AJ minus. Minus AJ minus is minus 6 times these things. Minus 6 is 1. But minus 6 is, annoyingly, equivalent to 1 mod 7. Because for us, this is minus 6J. Minus AJ minus. So I think that's equal to I. Yeah, so, and then AJ plus is the empty set. So these things do have the union I. Okay, so I've learned something important. J minus and J plus don't have to be the same size as each other. And in fact, if between them they've got an odd number of elements, then that was never really on the cards. I'm going to try a different number for A. Herb suggested 6, nothing wrong with 6. I think this is as far as 6 is going to get us in terms of understanding. Like, I think if we follow through, then yeah, these things are going to work out. But I'm starting to become worried that this existence of this minus A being equal to the number 1 is maybe causing things to simplify a little bit too much. So I'm just going to change A to 5 and see what that does to these sets. See if I can remember what I'm doing along the way. Yeah, Mountain Ash says 5 in chat. Let's try 5. There's a good lesson there as well, that finding examples is really hard work. We should try multiple examples anyway, right? I'll try 3, the James Prime. Yeah, no, I prefer that actually. I'm going with that. 3, right, good. So if I multiply these things by 3, then I get 3, 6, and 9. 3, 6, and 9. Oh, this is a much more interesting set. Look at that. 3 times I. 3, 6, 9. Okay, so this shows me that there might not be any pattern to the set. 6 was nice, it rewrote minus I backwards. Okay, so I want those J from I such that, so those J such that AJ is in negative I, and that is just the item 2. Whereas J plus is those J in I such that AJ is in I. Well, if you multiply by 3, the 1 and the 3 come round to elements of I. Have I got that right? There's an upper limit to how interesting these things can be, because I've only got 3 elements. I've chosen a very small prime 7. So I choose number 3. Ah, somebody's got a houseplant. Nice. Congratulations. What sort of houseplant have you got? Good. Okay. Right, let's try and understand this. It's going to spruce up the place. Don't forget to water it if it's one of the ones that needs watering, which is most of them. Don't forget to not water it if it's one of the ones that needs not watering, which is some of them. Try not to water all the other objects. Right, look, sort the objects into J plus, things that need watering, and J minus, things that don't need watering. The disjoint union is all of your stuff. And now, multiply the things. Okay, right. Good. So now I'm going to be interested in minus AJ plus minus and AJ plus. And there's some sort of magic that's going to occur down here, right? So I do AJ plus. If I multiply these things by 3, I get 3, and 3 times 3 is 9, which is 2. That's kind of weird. Minus AJ minus is equal to 3 times 2 is 6, which is... Oh, but there's a minus 1, so it's going to be 1. Okay, so these things give back a kind of different breakdown of I. That's weird. These things put together give you I, but with some stirring. Okay, want to understand that. And then maybe that'll be the last thing I understand. Ever. No, just for today. For people looking for the Discord, if you've just joined us, we have a Discord. Discord is over there. It's unofficial. In the sense of being... I've set up a Streamlabs for it, but it's not otherwise something I'm running. What am I doing? Oh yeah, I was going to try and work out why these things are disjoint. Right, because we multiplied everything by 3. If these things were... Yeah, I ticked this, but maybe I didn't understand it. So if we got something the same out from either our minus AJ minus A times one of those. Get everyone in Miro. Miro permissions are really weird. If you're using free Miro accounts, then the only way I can give you access to a Miro board is to give you access to all of my Miro boards, which I'm not going to do. So maybe I need to make a new Miro account just for the terrible outcome of this. Plant ID. I want a plant ID. Can I get Discord on here? Oh, I'm not logged in. Oh, okay. I'm not going to IT your plant. If these things had turned out to be the same number, then when you divide by A, and you'd say minus J minus, it's J plus. But that one's from... I don't get it. J minus is things in I. Oh, right, so these things are both... These things would both be in I, but there's a minus sign around. The minus sign is supposed to give us the other stuff. No, I don't love it. Don't love it. Yeah, maybe I'd prefer to think of this as ones where minus AJ is in I, because for every number, either AJ is in I or negative AJ is in I. So that helps me sort these things out and remember that there's a minus sign on the left. And then, does that help me show their disjoint? So if I got the same answer out, then I'd have 2 slightly different things that are in I. Yeah, with a minus sign in there as well. Okay, so these things are disjoint. These things are disjoints, no overlap. and they're both contained in I, because I want my minus AJ sets from this set, minus AJ is supposed to be an I, and over here AJ is supposed to be an I. Therefore, now they're not the same size, which is a mistake I made earlier. Not the same size as the mistake I made earlier. The union of these. Gosh, why has this step happened? See, this is just multiplying by 1, so you get loads of different stuff each time. So it's the sum of the unions, some of these things. And if those things made up I. Yeah, it's the kind of property, the set I satisfies multiple properties, and it's quite subtle. I and minus I disjoint and cover the whole thing. That's kind of 2 properties. It's quite hard to work out which one. Once I've seen there's no repeats, the kind of shape of a set of 1 element and a set of 2 elements is going to repeat over here. 1 and 2, so there are 3 things over here and 3 things over there. They're all in I by definition, because, yeah, right, okay, these things are all in I because they have to be. Oh, Math Games with Bad Drawings by, what's the name? Ben somebody, right? That book came out quite recently. I should actually get that book. There are 75 and a quarter games. Good eye. Okay, a whole bunch of multiplication down here. So then cancelling that gives that this is 1 more p, and so multiply over by minus 1 to the size of mod j again. And then Euler's criterion says that if you're using a prime p, this is the thing that you're calculating in order to talk about. If you've got an odd prime p, then this is the thing you're talking about for this Legendre symbol, the kind of synonymous. Then all in, there you go. Christmas. Right, Zoe's describing noughts and crosses. I'm gonna need a separate doc, I think. Is it on a torus? Is it on a torus? It's on a torus. Yeah, you're doing noughts and crosses on a torus because you're allowing winds like this, which if you rotate the board, let's rotate the board, is this. I think nothing's the centre, but also everything's the centre on a torus. I think the first player has quite a strong advantage. Yeah, the first move's kind of arbitrary, and it's like this, but you're allowing loads of wins. Sort of wherever this person goes, you can then... what can you do? Oh, you can do something amazing. This move is very powerful, right? No, maybe not. Maybe not. I can't remember how to win noughts and crosses on a torus. What kind of mathematician am I? First move's in the middle, and then does it matter where they go? Maybe it does, maybe it doesn't. There's kind of at most 2 interesting moves. At most 2. And then you can do something like... It's actually harder than I thought to set up. I was going to set up something that would call sort of 1 on both sides, but set up something like this? Yeah, there's no way this wins for them. Oh, are they quite close to winning now? We've got to go here. This feels winning. Can they win this? I think it might be a player 1 win. Quantum Donut, noughts and crosses. It's quite hard to draw a 3x3 grid on top of this donut. I'll give it a go. So I need to draw 3 lines to split it in 3. And one over here. Dot, 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 dot. And then some loops, I suppose, to split it into a grid. Yeah, centre bottom wins it, I think. Because Naught's going to have to go up here. It's a kind of forced play. And that's not a line, crucially. And then this is a win across this diagonal. And I should check what happens if the other game to explore is this one. I think it might be the same. I've got a feeling it's the same. Yeah, you can set up these triangles, and your triangle's kind of in free space. Kind of the this configuration threatens a win here, but also due to the new rules here as well. So this configuration seems really strong if you can set it up. And I reckon you always can. So, yay! Noughts and crosses on a torus. Now do 4x4. 4x4, probably a draw. You extended the symmetry, right? Extending the symmetry and repeating is really nice. It's exactly how this kind of torus model works, of having this side being the same as that side. Go off the edge, come back on the other side. It's the same thing in matrix determinants, right? If you're trying to calculate the determinant of a matrix, then you're supposed to do something using these terms, and then a minus sign on these terms, and then it's these terms but with a minus sign, and this is just whether or not the line is diagonal or backwards if you spin the thing around. So this is kind of equivalent to that. I don't know. Maybe I imagine things as donuts too much. Oh, okay. Yeah, it's discrete maths. Yeah, no, sorry. I'll take away the topology. Yeah, very, very, very cool game theory. Absolutely no topology there. Very cool game theory. Not wow. The opposite of wow. Take it away. Right, good. Too much topology. Too much. What was this thing actually trying to say? What were we trying to prove? Any set change. So then the rest of the lecture notes for this chapter just have so many like random set I. Turns up it's got half the elements in it. No overlaps. Yeah, it is the opposite of oh no, wow. I kind of feel like maybe? Because then the rest of these notes are going to have the parity of this set, and they've chosen the set really well. Oh, for the number A is the number 2. Oh, I do want to read this. How long have we got? Oh, it's 4 o'clock. Should probably wrap up in a second. How long is this proof? Proof's quick. Proof looks quick. Proof looks quick. Compute the parity of this with HA in minus I, where I is the first few elements. Right, P is this much. Oh no, I don't like this. R is not 1, 2, 3. What? 1, 2, 3. Oh, ooh. These are different cases for odd numbers, mod 8. I'm getting there. It's me. Right, here are your odd numbers. So we're doing, these are different, these are just to do, I think this is just to do different cases at once. Okay, your prime is 8k plus some smaller number. So then I is this many things. Minus I is the rest of them. The elements of that are precisely, oh my goodness, 2j minus I are precisely that half. Right, okay. Quantity T is the parity of the number of elements. Right. Oh, it's just counting. It's just counting now. It's counting. How many of them are there? Adding and removing an even number of elements from each end of the interval. Brilliant. So cases for R is 0, 1, 2, 3, depending on what the parity is. the number of elements is either even or odd, and then you get these cases. Wait, why do the cases not match up how I thought they would? Oh, right, so the even cases out here give us something where we have -1 to the power of an even number, which is 1, so it says it is a quadratic residue. 2 is a quadratic residue. If you are... Oh, these are, because of the R notation, these are 1 more than a multiple of 8 or 7 more than a multiple of 8. 2 is a quadratic residue in those cases, and it's not in these cases. Huh. So it's really weird. It doesn't construct a number that squares to 2 mod p. I thought it might, but it doesn't. It's sort of searching for one in a way. Maybe the set I can help me find one somehow. Maybe not though. This proof does not look quick. Yeah, I know. It's not got very many ideas. It's got a reasonably sized idea here, and it's got some stuff we were just doing here about counting. We were just doing this. We're looking at how large the set is, and I double all the elements. How hard can it be? Pretty hard. Yeah. Thanks for the follow, BC Aura. Nice to have you with us. One day I will learn. Here's the summary of today's live stream on quadratic residues. My attempt to learn them. So he's summed it up nicely. One day I will learn what a quadratic residue is, but today is not that day. This should be nice, right? It should be nice. A such that existent x with x squared equals a mod n. That's what it means for A as a quadratic residue. Quadratic residue mod n. There exists an x such that x squared is a mod n. Nice. Yeah, quadratic residues are fun. Thank you, BC Oro. Welcome to chat. Gauss has got a strategy for these. Gauss has got a strategy which involves... You can tell, says Gauss, if A is going to be a quadratic residue, mod p, a prime. If you choose just a set of numbers, split up half the remainders in the mod p world, call them I. Make sure that you've split it up so that I and minus I cover everything. You've got a positive and negative, but you can choose however you like. But people normally choose the first half to be the positive half, the second half to be the negative half, because it's also over here because of mod p nonsense. That's normally how people define positive and negative, fine, whatever. And then just count stuff, because it's Gauss. So we're just going to do something nice, like just counting things. Chat's correct, this is not an easy proof to read. Elements of J and I with 2J. I feel like if I understood this, I'm basically done, because this is the size of this, right? The elements where 2J is in minus I. Big proof that this is this relevant thing to calculate, and it just lines up nicely with a to the p minus 1 over 2, which is sort of Fermat's little theorem. For Fermat's little theorem reasons, was nicely related to being a quadratic residue. You're halfway there. What is this? So here is minus I. Why do I not like this? Doesn't look like minus I at all. It's over n, not a prime. How many quadratic residues are there? Ooh. The MIT Mystery Hunt now wants you to solve an IMO problem. Cool. Have fun. Yep, there's a counting argument, and I am not awake enough to do the counting properly, I think. Just to check, I'm going to wrap up in a minute. Somebody was asking for help with complex number homework. I don't know if they're still here. It was ages ago. Brood Quill, you still around? You want to talk complex numbers? You've maybe sat through a load of quadratic residues. I don't do a lot of homework help, but somebody asked nicely. It's polite to have a go, right? We did a sidetrack into somebody on the birthday paradox. A puzzle hunt at uni. Can't wait. Good. Okay, I'm not sure Brookwill's still here. We lost Brookwill at some point in the last 26 minutes. Okay, if you want to understand these lecture notes yourself, you can find them at the Oxford Maths website somewhere. I just downloaded them from like courses.maths.ox.ac.uk. Let me know if you understand them better than me. I think I've got some more work to do to understand quadratic residues. Take care, chat. Have a nice afternoon, have a nice evening. If you saw an advert today, you're supporting charity. I'll see some of you around at the Oxford Online Maths Club on Thursday. I might see some of you here on Sunday. Have a nice week, everyone. Bye. How do I end the stream? No, I've got a button for this. Bye.